All right. Hello, everybody. Welcome to Monday of week 8. We are looking to wrap up chapter 7 today, and we're going to start with some chapter 8 things tomorrow. Chapter 8 will be nice. We'll get our second chapter of applications to integration techniques. Now that we are all masters of most types of integration, we're going to see a bunch of things that we can do with them just like we did in chapters 5 and 6. 5 was techniques, 6 was applications, 7 was advanced techniques, 8 is advanced applications. So we'll just get to see some cooler and cooler stuff that we can do with integration here coming up in chapter 8. So in chapter 7 today, what I'm kind of hoping is going to happen, or maybe I should actually say this before I actually get started on some of my things here. I think that this week I am probably going to do 3 lectures, but I think that they all should be a little bit shorter than usual, hopefully. I know I'm sitting here talking slow, talking about plans, but I could be talking about content here. But what I am thinking is that we want to hit improper integrals today, arc length tomorrow, and then area of a surface of revolution on Wednesday. My ideal plan would be if I could just do each of those 3 things in an hour instead of doing 2 videos over an hour and a half. Then that will be still the same amount of video length for all of us here, but a little bit more compartmentalized. So I am hopeful that our topics here this week will be a little bit more manageable to where we can handle doing slightly shorter videos than me getting all lengthy here. So to that end, I'm going to get started here. So in this section, we're going to basically look and see what happens when infinity starts creeping into our integrals. Now, on the one hand, I hope that you guys are all down with a pretty broad concept that, in a sense, what calculus is the study of infinity, right? When we talk about limits, we talk about going places. We talk about either going infinitely far or getting infinitely close to something. Right? When we talk about derivatives, we talk about what is the slope between 2 curves and the way that, or sorry, the slope between 2 points on a curve. And the way that we actually manage to compute that is we start with 2 general points and we move them infinitely close together. When we talk about Riemann sums turning into integrals, we talk about computing a finite number of subdivisions of an interval, and then we allow the number of subdivisions to tend off to infinity, so that we get infinitely thin slices of Riemann objects. And then when we add up an infinite number of n-dimensional Riemann objects, we get an n plus 1 dimensional object, right? So everything about calculus is already directly surrounding the concept of infinity. What happens when you take something infinitely far, when 2 objects get infinitely close, et cetera, et cetera. These are like the heart of the questions that we answer with calculus. Today we're more formally sticking infinity in there and literally saying like what happens if the numbers you're working with are infinity rather than just the concept of infinity underlying our actions here. So I think 2 good, very basic things for us to think about are, 1, 2 ways that we're going to encounter infinity today. One of them is going to be infinity being in the bounds of the integral, right? So the integral from 1 to infinity of 1 over x. This is a more direct version of infinity. The other place where we can end up seeing infinity is in the integrand. Notice here in this integral that we're looking at, there is no infinity that you can see. There's no infinities here, no infinities here, no infinities here. Okay, that's an infinitesimal, so I guess that qualifies. But the point here is, and by the way, I'd like to point out to you, this has to do with a question I'm going to be ditching from our test that we just took because I noticed a stupid thing that I did on there. Is you should notice that although our bounds here go from 0 to 2, we're clearly crossing an asymptote that occurs at x equals 1. So our y values here are going to decay down to negative infinity and then pop back up at positive infinity and keep going over the interval of interest right here. So that's going to be weird. That's bringing in some sort of like y values that are infinity are here. A y value of infinity. Our heights get infinitely tall over this interval of interest, right? Here our width will get infinitely wide, and we want to end up making statements about what's going to happen with these guys. So these are really the 2 different ways that infinity is going to crop up. One thing I'll say before I move away from the screen is, in this case, it's obvious to you that you've got infinity to deal with because it's staring you right in the face. In this one, it's a little bit less obvious. One of our new responsibilities, according to this section, is we always need to stop and ask ourselves, do we experience any vertical asymptotes over the bounds of integration or not? That's now a new question that you are, in a sense, required to think about before you perform any integration process. Because we're going to see here, it's going to give us a little bit of trouble right there. And I'm just going to say here, as in holding with my statement, I think I can do 3 shorter lectures this week. All this will be pretty easy to manage. We just need to pay a little bit more attention. And by that, I specifically mean this case here, paying attention to saying, do we experience a vertical asymptote over our bounds of integration? If so, we need to stop and be more careful. That's the paying a little bit of attention that we need to do. And the other thing is that we just need to be all right with handling limits here. We want to be a little bit careful with our limit evaluation. I'm assuming that most of us are going to be mostly good to go with the limits. I'm also assuming a couple of you are going to evaluate some limits backwards. And so I want to make sure that we avoid doing that with some smart limit manipulation here. So first things first, I want to start out with these examples. The book does these examples. It doesn't matter. These examples are too important for me to not do them. I literally have to do this or I have not done my job in discussing improper integrals here. Man, it looks like I'm just dropping a ton of frames all of a sudden. My stream this morning went perfect and smooth, and now I'm just dropping a ton of frames here. Hopefully this isn't too choppy. Um, I wish I would ever know what influences this. Perfect internet this morning for my one viewer. Now I've got several. Choppy internet. So assess the convergence of the following integrals. Good, Coffee Gopher. Thank you for the vote of approval right there. And so one thing I'm doing right now is I'm kind of skipping some definitions that the book gives, but I think you're going to be very, very down with these ideas of convergence and divergence here. So what we want to do is really just use these examples to get comfortable with some of the notation that we want to use when we're evaluating these guys. So I'm going to give myself a look. Okay, and we'll start today by yelling at the computer. Computer, am I allowed to write with my stylus? Yes, okay, now I am. All right, so our first couple examples here, as I said, these are very standard. The book does them both. I don't care if the book does them both because these are sort of like some pretty core quintessential examples associated with looking at convergence and divergence of improper integrals here. So what I want to think to myself here, first of all, is when I see both of these integrals, I can see the antiderivative is very, very easy for me. The antiderivative of 1 over x is going to be the natural log of x. But what I'm going to do first for myself here is I'm going to rewrite this a little bit differently. In general, what we don't want to be doing is we don't want to be writing this as like, we could be thinking of this as like f of infinity minus f of 1. But this is bad notation right here because we don't want to think about infinity being like literally a number that we plug into things, right? So technically that's what we should be getting out. The antiderivative at infinity minus the antiderivative at 1. But infinity is not a number that you plug in as a function value. We think of these in terms of limits is how we notate these typically. So the first thing I'm going to do is I'm going to rewrite this in terms of a limit statement. I feel like every time I've ever swapped out a variable to hold my infinity number, I don't know. This does not matter. I've always used b. I noticed that our book uses t for all of them. Really doesn't matter here. All I'm going to do is just rephrase my statement like this. What this allows me to do now is interpret everything just associated with the integral as totally normal. Then this allows me to think about the limit, the infinity part happening later. So this allows me to sort of separate off the infinityness from the integralness a little bit right there using that notation. So now I'm going to go ahead and retaining my limit notation. Here we should be getting the natural log of x evaluated from x equals 1 to x equals b. Again, I'm going to keep on ignoring the limit part of this. It's going to hang out front this whole time. B is going to go to infinity. And here what I can see that I'm getting is I'm getting the natural log of b minus the natural log of 1. I know that that's 0, so I'm not too worried about this. So now this is really just saying to me, what do we get from just about, seriously, where's the bottom of my page at? Oh, I guess I kind of want this up on this page. I'm going to leave that guy right there. So what this is now telling me is that we are getting limit as b goes to infinity of just natural log of b. And so this is basically just saying if you plug in an infinitely large number into a natural log, what are you going to get? And so here I'm going to say that this diverges to infinity. That's my kind of final answer right there. We are diverging. Our value is getting infinitely large. If you plug in infinitely large things in a natural log, it is true That natural log crushes things down, sort of like a square root does. But if you plug in infinitely large things, you're going to get out infinitely large things from that natural log function right there. So notice here that I used a limit to handle that infinity term. While it's appropriate to write this as the boundaries from being from 1 to infinity, it's going to be both more appropriate and better for you to keep track of your terms if we express our infinite parts as limits sitting outside and or sitting out front. So notice here, infinity I wrote as a number, b, but I'm letting that number go off to infinity. It's really like b is sort of a middleman that we're introducing so that we can deal with the idea of integration separate from the idea of the limit going on in this problem here. So what we're saying here is that the area underneath 1 over x from 1 to infinity is infinite, right? So that just looks like this guy right here. And what we're saying is that it turns out that's an infinite amount of area. Well, notice over here we're barely doing anything different, right? That's our 1 over x squared. It's like the same thing here. I literally don't know how to draw these pictures so that one more looks like the other. And so it looks to me like we're also going to be getting another infinite tail out here for this 1 over x squared. You should notice that we're going to compute this integral a little bit differently here because we should be thinking of this as the integral from 1 to infinity of x to the negative 2 is going to be my little bit smarter way for me to phrase this for myself. So I'm now going to do my same moves over here, right? This is a limit statement. B goes to infinity from 1 to b of x to the negative 2 dx. And now let's go ahead and actually evaluate this guy here. When I evaluate this, limit as b goes to infinity of, I'm going to add 1 to my power, so I'm going to get x to the negative 1. I know that this would, if I took the derivative right now, a negative would pop down, and I don't want a negative, so I'm going to introduce a negative to cancel that guy. So it looks like this is my antiderivative. If I take the derivative, negative 1 times negative 1 is positive 1, same coefficient. Subtract 1 from the power when you take a derivative, I get that power at negative 2. So it looks like we have our antiderivative, and we're going to evaluate this guy from x equals 1 to x equals b. And when I do this, it looks like I'm getting here negative 1 over b minus negative 1 over 1. So now what are we getting here? It looks like I'm getting here. Notice if I evaluate this limit as b goes to infinity, this term is going to go to 0. So this is weird. My pictures look identical for these two problems. Right? My pictures look the same. I can't really draw 1 over x and 1 over x squared different than the way that I drew them. But it seems like 1 over x is decaying slow enough, it's approaching the height of 0 slow enough, that it actually accumulates infinite area on its way down to touching the x-axis. It never touches the x-axis. But we know that both these things have a limit of 0 as x goes off to infinity. So as the 1 over x function gets closer and closer to a y value of 0, it's actually accumulating infinite area along the way. On the other hand, 1 over x squared seems like it's decaying to 0 faster than 1 over x, and therefore it actually only accumulated a finite amount of area. In fact, and not just a finite amount, like 1, like an area of 1 was accumulated between 1 and infinity out here. So this hopefully to you is like a surprise. I mean, this seems weird to me that we can get answers that are wildly, wildly different between 1 over x and 1 over x squared, considering when I draw one lobe of each of their functions, I've drawn them identically every time I have for my whole life. But it turns out the area under one of them is an infinite amount of area, and the area under the other is a finite amount of area. And not just finite, but like literally just 1 is the total area underneath 1 over x squared from 1 all the way to infinity. And so definitely a surprise. Yeah, that's weird. But again, just following some limit statements here, hopefully you all feel pretty comfortable with this, even though it's our first one that we're taking a shot at right here. So hopefully this leads us now to a very natural question of, well, what's up with other values of, or what other powers on x? So this 1 over x to the p. The reason that we're doing these, even though the book does these exactly, is because these are very important for some comparisons that we're going to be making out in chapter 11. These are going to become called p-series when we do the sum instead of the integral here. The sum of 1 over x to the p And we want to be saying, does this sum get infinitely large? Or does it not get infinitely large? Does it diverge or does it converge? And we want to come up with a rule associated with that, associated with the size of p here. So let's play the same game, but notice in this one we're doing this for a general power on x instead. So the two moves I'm going to make for myself to help myself out here are, one, I'm going to rewrite this limit statement, or as a limit statement, right? Rewrite my infinity bound as a limit. The other thing I'm going to do for myself is I'm going to rewrite this as x to the negative p, so I can do my integration a little bit more easily for myself here. Um, and when I do this, what I'm seeing here is we should be getting limit as b goes to infinity. I'm going to add 1 to the power, so I'm going to get negative p plus 1. But if I took a derivative, I'd get a 1 over negative p plus, or excuse me, I'd get a negative p plus 1, so I need a 1 over negative p plus 1 to sit right out in front as my parameter, or as my coefficient right there. And this is the guy that we will evaluate from x equals 1 to x equals b. So let's go ahead and see what we get from this guy here. We should be getting this 1 over 1 minus p. Notice, by the way, this is just a constant multiple. This does not affect the limit. It has to do with b only. The bounds of integration have to do with x only. P is just a constant in this problem. So I'm going to pull out that 1 over 1 minus p part right there. And it looks like what I should be getting here is the limit as b goes to infinity of, I should be getting b to the negative p plus 1 minus 1 to the negative p plus 1. All right, so I've plugged in b for x and I've plugged in 1 for x for my lower and upper bounds here. So what's happening here? Not quite clear to me. Not 100% clear to me what's happening. So I've got a 1 over 1 minus p here as my constant coefficient. And what we need to decide what's going to happen here is for different values of p, what kind of result am I going to get when I let this b go off to infinity here? And so here's the things I'm noticing. I've got myself some room down here. Let me do a thing down here. Notice that if p is, for example, then we would be looking at 1 over 1 minus p, limit as b goes to infinity of, I'm not worried about that p being 5 yet. Okay, of b to the negative 4 minus 1 to the negative 4, right? So I've plugged in p equals 5, at least over here. Now, infinity, the negative 4 power, this is really going to be like a, I'm going to say this here, limit as b goes to infinity of 1 over b to the 4th minus 1. Notice here as in b goes to infinity in this case, this term is going to go to 0. And we're going to subtract 1 here, so we're going to get a negative. And so if p equals negative 5, then we're really getting 1 over 1 minus, or p is positive 5. And I should be just getting my answer here of 1/4 as my final answer. So it looks like when p is 5, we converged. However, notice that, for example, if we do something like if p equals negative 2, then we're going to get 1 over 1 minus negative 2. Limit as b goes to infinity of b to the, now, if p is negative 2, let me come back up here. Notice if p is negative 2, then we're getting overall a positive 3 power up here, right? P is negative 2, then overall I'm getting a positive 3 power. Well, you should notice right away that this is clearly diverging. B is going to infinity. B cubed is therefore going to be infinity. Infinity minus 1, still infinity. And we're only keeping 1/3 of that. So it's going to be 1/3 of infinity minus 1. So here I'm going to say my answer is this diverges up to positive infinity. And so notice here that the size of p determines our convergence or our divergence in this situation. So let's scroll back up here and see what were our like kind of comparison things here. It seems like what happens here is if we end up dividing by b to a power, b to a positive power, then when b goes to infinity, that's gonna decay to zero, and we're just gonna be left with our 1 over p minus 1 term, right? We're always gonna be subtracting off 1 for a negative, so that would always flip our sign over here. On the other hand, if we end up with a positive power overall on b, then as b goes to infinity, this will diverge off to infinity. So it seems here to me that like when p is equal to 1 is a special location right here. P equals 1 is where we experience this transition from the divergence to the convergence, because when p is equal to 1, that's right when the power is 0. And we know that we care about powers being more than 0 or less than 0 for our convergence out there. So let's see what happens if we kind of try and group up what we're saying right here. It looks to me like we can conclude here that the integral from 1 to infinity of 1 over x to the p dx is going to... Now, it looks like over here we chose p to be large values, larger than 1. That we were converging, and what value did we converge to? Well, b to the negative fourth went to 0. I just got really a negative 1 out of this entire parenthesis statement right here, a negative 1. And negative 1 being multiplied in here gives me 1 over p minus 1. Notice it just flipped that denominator right there because we multiplied by a negative. Notice that we did an example where p is equal to 1. This is our p is equal to 1. This is 1 over x to the 1. And this guy diverged to infinity. And also, when we used a p value that was less than that, negative 2, we also diverged. So whenever we have a p value that is less than or equal to 1, then we are going to see this guy go ahead and diverge on us right there, right? This is a converge scenario there. This was a diverge scenario whenever we had that p, the power, being less than or equal to positive 1 right there. And so this is interesting. This is interesting to see that families of functions might have areas that tend off to infinity with certain parameters and that converge to finite values with other parameters that are out there. And so again, this is going to be something that we're going to be very interested in because our upcoming topics in chapter 8 are going to be interested in things like we'd like to see for our probability unit having total area under the curve being exactly 1. We need convergent integrals, even though a lot of our supports on our probability functions go from negative to positive infinity as bounds. We still need the overall area under the curve to just be 1. Also, this is going to be kind of setting ourselves up for a lot of chapter 11 discussion. We're going to come back to make a statement that looks just like this, but with sums instead of integrals in chapter 11. These are going to be called p-series, and they're going to be super important for us to making comparisons to other types of sums that we see out there, because already we're able to kind of state everything we need to know about these power p functions here. Later that will be called p-series when they're written as sums. And those will help give us a sort of a boundary for other things of saying, we know that things are bigger than this or smaller than this, therefore, it'll help us make some comparisons. So again, our kind of warm-up ideas here are just that. One, this is weird. You should think it's weird that sometimes we get infinite area underneath an infinite amount of curve. Other times we get finite area under an infinite amount of curve, even when the functions very similarly match. The thing that we're kind of noticing here also is this has to do with the rate at which we tend towards 0. Both of these functions have the property that is the limit as x goes to infinity, y goes to 0. That's true for both. Both of these are tending down to almost touching the x-axis as x gets bigger and bigger and bigger. But because 1 over x squared does it fast enough, it converges on heights close to 0 fast enough that it doesn't accumulate infinite area. And because 1 over x does it slow enough, it does accumulate infinite area along the way. And it's weird, and I think that we can judge that there's different rates of decay here, but to see that those rates of decay are on either sides of the fence as far as infinite area and not infinite area is kind of a surprise right there. So even though this is a really basic example, this is a good and basic surprise right here to see, to hopefully motivate the interestingness of this section here. So let's look at our next example here. Perhaps we might see some infinity in both bounds. I gotta just give myself a whole page for everything from now on here. So this problem right here, nothing too special. The only thing that we want to do here is be a little bit careful with our notation with this guy. And so what I do want to do in general, whenever I have infinity in both of our bounds, is always split this up into two integrals where we always have infinity in only one of our two bounds. So in general, you should just be thinking to yourself, oh my gosh, it's the straightest line I'm ever going to draw ever on my digital stylus here, is that we are just interested in breaking this up any old location. I'll just call it A right here. We can form, instead of an integral from negative infinity to form a negative infinity to A, and then an integral from a to positive infinity out there. This is generally a good way to make sure that you only have one infinity to deal with at a time right here. And you're allowed to do this any location that you want A, as long as we're making sure that A is not a place of like a discontinuity. Then we got to be slightly more careful there. So in general, this is like pick a nice point for you to just cut this thing in half so we can deal with infinity one at a time here. Negative infinity once, positive infinity once. In general, I think that the easiest move to do right here is always to say, we notice, for example, that this function is continuous everywhere. X squared is continuous. E to any power is always continuous. Therefore, the product is continuous. I can pick anything, and so just pick the number that's nicest to you. So I'm obviously going to pick x equals 0. So my first move with this guy is always going to be, whenever I see the double infinities there, is to rip this apart into two different statements. And now I'm going to be able to manage my two infinities separate from each other. This is just a good move. This is great bookkeeping right here to be smart about this. So the advantage here is a bit of a notational thing, CopyGover. So it's really one of these things where it's like, do you really want two different values out there floating around that you're evaluating two separate limits? And so this is, in a sense, just saying deal with one limit with one infinity bound and then deal with another limit with a different infinity bound. One's going to positive, one's going to negative. What we don't want to do is do things like have b go to infinity and then negative b also go to infinity or something like that. This is just good notational practice. The other reason why this is important is because if there was, for example, a vertical asymptote at x equals 0, then we'd need to be having a limit associated with the 0, because this limit would have to be approaching 0 from the left-hand side. This limit would have to be 0 approaching from the right-hand side right here, since this is all of our positive valued stuff. And so this is really just a bookkeeping thing to help prevent you from having like limit statements on limit statements with several variables being limited different ways and stuff like that. This is just saying make your work easier by writing slightly more. I think this is a fair and smart trade-off right here. So I am going to do this as I'm going to do just kind of make up some things for myself here. I'm going to let a go to negative infinity and write this as a to 0 x squared e to the negative x cubed dx plus limit as b goes to positive infinity from 0 to b, x squared e to the negative x cubed dx. And again, this is really just saying don't over infinitize yourself here. It's good to rip things apart for yourself so that you can deal with individual parts at a time. The good thing about doing this integral here is I do think I get a common set of substitutions that I need to do. I'm noticing that there is an x cubed in here times some x squared stuff. So I think it's going to be reasonable for me to be doing a u sub that looks like this. All right, so my u sub is going to be the same for both of these guys right here. I just want to keep track of my variable bounds with their infinities slightly differently here. So what it seems like I'm getting now for myself is the limit as a goes to infinity of the integral of x squared dx just became 1/3 du. I'm going to bring that 1/3 all the way out since it's just a constant multiple. It looks like we're just getting e to the negative u is all that's left. Plus, similarly, the 1/3 is going to be there. Limit as b goes to infinity of 0 to b of e to the negative u du. Same thing. And now we can go ahead and evaluate our limits, then do the integrals, right? It's always good to save the limits. Oh, wait, sorry, I think I said that backwards. We can now do our integration and then hit them with the limits that are appropriate here. So I'm noticing this 1/3 is cruising for a ride on the whole dang thing out here. We're going to get the limit as a goes to infinity of negative e to to the negative u evaluated from x equals a to x equals 0. All right. And now we're cruising. Now we just want to convert to x and hit ourselves with some limits here. Wait a minute. Haven't I dropped my... I have. Okay. A is go. So this is why I need to not be dumb here. A is going to negative infinity. I dropped my negative on my A's here. A is going to negative infinity. Negative infinity. Negative infinity. Negative infinity. And here this should be negative e to the negative x cubed, evaluated from x equals a, x equals 0. Losing track of my infinities here. All right, so it looks like we are ready to make some action happen here now on this guy. So I am seeing here for our left half and our right half. On our left half over here, I'm going to be getting 1/3 of the limit as a goes to negative infinity. And by the way, notice here I'm also popping out a negative on each of these guys right here. This should be e to the negative upper bound, 0, minus e to the negative lower bound. Over here, I'm getting e to the negative upper bound minus e to the lower bound over here. Now, what is going to happen when we do this guy here? Well, what I'm seeing is this. I'm going to get a negative 1/3 right there. I can see it. That's going to be a 1. Notice over here, I'm going to throw in a negative massive number into a. Right? So a is some negative massive number. I've got 3 copies of the negative. That negative is a 4th copy of a negative. That's a positive on the infinity here. So it looks like I'm getting something like this. Notice I'm getting negative 1/3 times negative infinity. Looks like our left half is diverging to positive infinity. So I want to say one thing before we move on here. I don't even need to finish this problem is the thing that I want to say. If I'm trying to assess the convergence or divergence of this integral, just knowing one piece of it diverges makes me know that the entire thing is going to diverge. And here's the reason why. There is no addition or subtraction of infinity that you could ever do that you could convince me is going to perfectly cancel another infinity. Infinity plus infinity, infinity minus infinity. I can never say that infinity minus infinity is going to be some convergent number like 7. I never know that. And so I don't care what we get out of this guy over here. There's nothing that you could do to convince me that we're not going to end up with infinitely large values overall. However, for the purpose of this problem and seeing a result, I still do want to look at what the right half of our graph looks like so that we can look at this graphically and see that we totally agree with what just happened here. So I'm going to keep going, but I want you to know that if your job is to assess convergence or divergence, just finding one chunk diverges, you're done. You can say because the integral diverged from negative infinity to 0, the integral must diverge from negative infinity to positive infinity. That will be a completely true statement right there. But let's finish this just to help ourselves out graphically to see, so a kind of nice comparison here. There's still things to be learned about this problem, even though we have the answer. Over here on the right-hand side, I'm now going to get this minus 1/3. But notice what's going to happen over here. Here, b is a positive infinity. We're going to cube that, but take the negative. So this is now like an e to the negative infinity minus 1. And you should be seeing here, if we plug in infinitely negative numbers as a power on e, this is like 1 over e to the infinity, which is a lot like 0 there. So what I am seeing here is that we're going to be getting something that looks like this right here for 1/3 for the right-hand side. So I'm seeing here two statements I can make. Negative infinity to 0 of x squared e to the negative x cubed dx diverges to infinity, but the integral from 0 to infinity of x squared e to the negative x cubed dx looks like it's really just equal to 1/3. But I do want to say diverges overall, right, with the full bounds from negative to positive infinity right there. So let's go pop over to Desmos real quick and see a graph of this guy so that we can see exactly why we got this left half and this right half that looked like we did. The graph of this, you're going to look at it and be like, oh, okay, that makes sense. So if I pop over to my browser here, let's graph this guy. We were looking at x squared e to the negative x cubed. And here is what our graph looks like here. Notice here that on the left half of our graph, we are getting right away just huge amounts of area over here, right? And in fact, I guess what I should do is say 0 is less than this, is less than, oh wait, I guess that can't, oh, whatever. I'm just going to do, wait, will this work here? No, I wanted to just, sorry I made you mad, Desmos. Okay, we'll go back to the way it was. I just wanted to get like area underneath, but apparently I'm too dumb to do that right now. So the point is, we can clearly see the infinite area under the curve off on the left-hand side. Here is our diverging half. But hopefully it's pretty believable to you that this, and in fact, by the way, boy oh boy, doesn't this look like the normal curve that we've been talking about for e to the negative x squared for the last couple weeks out there? And hopefully you can believe that like this thing looks like it decayed pretty hard to 0 right here. We're not really accumulating any more area out there. We are technically, but not an infinite amount. And so it looks like just this area right here on the right-hand half of our graph as we go all the way off to positive infinity is going to be 1/3. So I think you can believe just looking at the graph that the left half of this function has infinite area. The right half of this function does not have infinite area underneath the curve. But therefore, the overall amount of area has to be infinite because the left half was right there. So hopefully you can see this graph very much agrees with exactly the results that we just got there. So let's pop back over to Word and keep her going here. All right, so let me now show you about the problem I screwed up on our test that I have to discard before I can wrap up grading these things here. I put a problem on the test that was basically this, and I know that a bunch of you just did what it seems like you should do, and you got the same answer that I first wrote down as my first answer before I realized I was doing something stupid. So what's our issue with this guy right here? Well, I know what the graph of this thing looks like, right? I know that we have at x equals 2 an asymptote. This question is asking me for the area between the curve and the x-axis from 1 to 4. Well, you can hopefully imagine that this is a bit problematic, actually. So a couple things. One, we've already seen that this 1 over x function seems to accumulate infinite area. Two, we can see that we are tending off towards a positive and a negative y being infinity value that's sitting out there. Right? So what I really need to do here first is do this wrong. I'm going to do this wrong first. So let me do this whole dang thing in red right here. So there's my bounds, 1 to 4. We do have a vertical asymptote in that chunk, and that's going to make a problem for us. So everything I'm going to write in red is a wrong answer to this. It's not what you should do here. But I'm going to do it this way anyway. What I'm kind of seeing here real quick is that we should be getting the natural log of x minus 2 evaluated from x equals 1 to x equals 4. This should be giving me the natural log of 4 minus 2 minus the natural log of 1 minus 2. Fortunately, we remember absolute values are there, so that's at least not a problem. And it looks like all we're getting here is natural log of 2 minus natural log of negative absolute value of negative 1, which is just natural log of 2 minus natural log of 1. And since natural log of 1 is 0, that's just giving us natural log of 2, right? So this would be a very good wrong answer for this. And hopefully you are okay with the fact that, like, I don't know, this is getting up infinitely tall and infinitely low here. I don't think that we're just getting the natural log of 2 as our total amount of area right here, considering we're going to go infinitely up and down with a function that we've already seen diverge off to infinity here. So now let's do this the correct way, and let's actually break this up over the where we see that asymptote. Yeah, well, that was a squared though, right? That squared thing was converging much quicker. It was decaying to the x-axis quicker. And hopefully, at least what you should be thinking right here, Coffee Gopher, is these get tougher to guess. You can look at a graph and just, it's no. Yeah, with your sample size of 1. Yeah, exactly. Good guessing right there. But yeah, guessing these is hard. Is a good lesson to learn here. So what I am going to do is I'm going to break this up from 1 to 2 plus from 2 to 4. And what I know is happening is I know that there is some asymptote, vertical asymptote happening at x equals 2. And so I'm going to want to handle that appropriately with some limit statements here. So what I'm seeing here is we should be getting here the, and so notice here, I can't straight up plug in 2 into this function. And when I get my natural log of 2 out, I can't do the natural log of 0. That's also an undefined quantity here. So what I am going to rewrite this as is the limit as b goes to 2. It's going to 2 from below, right? Because we're interested in the values between 1 and 2. So this should be the values that are less than 2. This is going to be the values from 2 to 4. So the two values of interest are going to be above 2. So here we're going to limit towards 2 from above, right? And this should be my 1, 2, 2 of 1 over x. Oh, nope. Can I redo that? This over and over and over here. That's fine. Okay. I don't see why it's okay. Okay. I guess I'll write it again. I gotta get this dang undo redo button figured out here. All right, so I'm going to rewrite this then as, and I'm going to change my variable that I just set up here as a goes to 2 from below, because this is values below 2. B will be the one that goes towards 2 from above, because all the values here are between 2 and 4, so they're greater than 2. Integral from b to 4 of 1 over x minus 4 dx. And so what are we going to get here? We're still going to get our same type of results here. Right? We just got a little bit more writing to go with them. So I'm going to just write this one here. This should be a minus 2. Oh gosh, I can't risk undoing. Minus the natural log of 1 minus 2. Now notice this guy right here right away. Absolute value is going to say 1 minus 2 is negative 1. Absolute value of negative 1 is positive 1. Natural log of positive 1, this is going to be 0 right there. So all we've got to do is figure out what's going to be happening as we approach 2 from the from below here. So as I approach 2 from below, that means I'm getting numbers like 1.99999. That should be giving me a negative, very, 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 very small number. Absolute value means it's a positive, very, 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 very small number. And what we know about natural log is that the closer that you are to the y-axis right here, these are when all of our various values are very, very negative down here. So this should be giving me some form of negative infinity right there is what I'm getting out of this natural log value right there. If I come over here and check out my right-hand half of things, I'm going to see something very similar. Oops, why did I switch right here? That's a 2. That's a 2. All right, so it looks like what we're going to be getting here is we're going to be getting the limit as b goes to 2 from the right of natural log of 2 minus natural log of b minus 2. Again, what you can see here is natural log of 2 is just a number minus, again, b is going to be a number just barely bigger than 2, 2.00001. So this is going to be like the natural log of 0.000001. And again, when we are looking at that natural log, okay, I'll get my backwards hands here. Natural log does stuff that looks like this. We know that as we're really, really close to the x-axis is when we're really low, right? So we have really small y values when we are close to the x-axis on that natural log function. So here again, this is basically like me getting like a natural log of 2 minus, and here I'm basically getting like a negative infinity. So like a natural log of 2 plus infinity. So right here I'm just trying to suggest, I suppose, that our that's interesting. It dragged that infinity with it. That's weird. That here we're getting a negative infinity for one part, which we expected, right? We're getting negative infinity for one part. We're getting positive infinity for another part, plus a little natural log of 2. Who cares about that? So we got negative infinity plus positive infinity. I have no way of judging that, right? We have no way to kind of directly compare these guys right here. So it seems more appropriate for us to suggest that we are diverging here since all of our parts came out as infinite in size here, right? So here it looks like this is a diverging integral right here, rather than us just doing it the wrong way like we did in red and directly evaluating, because this ignored a lot of our action associated with those infinities out there. Right? Another example that I thought was good here that I think we should look at is one. Do I have an eraser here? Can I erase this? Hey, I've never done that before. All right, let's compare some things real quick, and then we'll do a comparison. I guess we have comparisons that are remaining here. One of the ones the book wanted to show right here was evaluating from 0 to 1 of natural log of x, and that actually has a lot to do with what we just did, right? We looked at these really small values here. At 1, we're at 1. Oh, sorry, I'm thinking of the wrong function right there. At 1, we have 0. And so we are interested down here in this area of interest that's right here. Now, the thing that I thought was interesting about this problem is that in this problem here, the infinity is in the integrand. My first thought with this one is I know an inverse function for this, so I should be able to set up an exactly equivalent picture for this, right? I know that this getting really close to the y-axis is just like our e to the x function getting really, really close to the x-axis out there. Right, there's our e to the x function. we could instead be thinking about what does this area look like right here. This is just an alternate way to rephrase the exact same amount of area that we're going to get. So my claim is that these two should be essentially exactly equal to each other. The only difference is that if you take a look at their graphs, you should be able to see that this will be a negative number and this will be a positive number. But other than that, we're going to get equivalent things here. So this is just a nice, nothing too crazy right here. The limit as b goes to negative infinity of b to 0 of e to the x dx. We can do our quick little integration and get e to the x evaluated from x equals b to x equals 0. Limit as b goes to negative infinity. And in this case right here, right, we did our integration. We got e to the x. So we should be getting our upper bound minus our lower bound. So limit as b goes to negative infinity of e to the 0 minus e to the b. And that's going to be giving me limit as b goes to infinity of 1 minus e to the b. And what we can see, wait a minute, where's my, oh, I did it again. I was like, where'd my negative go? I dropped my negative on my limit statement right there. And so here, what we can see happening is we're going to be getting our 1 minus e to the negative infinity, in a sense right there. E to the negative infinity, this is like our 1 minus 1 over e to the infinity. That's just going to be giving us 1 right there for our final answer. So the book does example 8, I think, out there, and they show that this answer for this integral is negative 1. It's just negative because it's below the x-axis. This one's positive 1 because it's above the x-axis. And we can graph these also in Desmos and kind of show that we're going to get these exact same things over here. So they were looking at natural log of x, but they were wanting this to be as a y value. How did I do this a bit ago? We're looking at this for our, I wanted, yeah, I wanted this. No, I'm being dumb here. How did I set this up? I literally just did this like an hour ago, and now I can't think of it. In any event, e to the x right here. Shouldn't I just be able to say, like, the y value should go from 0, let's equal e to the x, less than y. Is that not like a reasonable statement for me to make? Hey, there's the region of interest right there. And then over here, we should be able to say something like, I want a similar statement here. Oh. And then I want this to be the 0. Is that not the case? Whatever here. I'm being dumb now. I don't know why this is not what I'm thinking of right there. In any event, okay, I'm done being stupid. What you can see is that the area shaded underneath here is exactly the same as this area that's shaded underneath right here. They're the same regions. One is just a negative area because it's below, one's a positive area because it's above. So I do want us to think about things like if you need to understand the size of some integral, that maybe you can't do it. And therefore, it matters that maybe we can rewrite regions of interest in terms of other regions of interest like we're seeing out here, right? So this integral right here, being able to re-express it as an alternate region might make it easier for us to discuss its convergence or its divergence out there. So let's look at one last thing here, and this is like a hugely important thing coming up for chapter 11. What we really need to know about, we still want to make statements about integrals we can't do, right? So here's an integral we can't do. We've talked about this when I brought this up like literally every lecture for the last like 10 lectures by now. E to the negative x squared. We know that we cannot directly evaluate this. We just can't do it. But what I still want to know is things like, well, like how big is it though? Like, is it infinitely big, or does it converge or does it diverge? I can't just directly integrate it. So I'm going to call this thing f of x here. I can't directly integrate that f of x function. So here's my deal. 1. If I can find a function that's above our f of x function for the entire boundary here from negative infinity to positive infinity, and if this other function I can find also converges, then it must be the case that our function of interest converges. This is like me saying, listen, I've got something that I know is bigger than the thing that you've got. We have no way of measuring the thing that you've got. The thing that I have, though, I know it's bigger than your thing. And my thing has size 20. It converges. Therefore, you should know that your thing has at most size 20, because we know that my thing is bigger than your thing. And the good thing here is that the thing I'm talking about is the function itself, not the integral of the function. If I can find a function that is above your function everywhere, then there's more area underneath the above function than the below function. And if the area underneath the above function converges, then the lesser area beneath the below function must therefore also converge. So if we think that this guy converges, then we should be able to find a function that is above it for all the region of interest, and then be able to verify that that above function converges, therefore ours converges. Alternatively, if I can find a function h of x that's below our function of interest, and where h of x diverges, then this is saying, listen, I've got something that I know is smaller than what you have, and even my thing diverged, so yours is going to have to diverge. But notice that if you have something that has infinite area underneath, and we know that mine is less than that, I can be less than infinity and still be infinity, or be less than infinity and be finite. So that's not helpful to us. Similarly, if you know that your function that you're trying to judge is greater than some other function, and that some other function has an area underneath it of like 6, well, 12 is greater than 6, but so is infinity. So knowing that it's bigger than something that converged doesn't help. Knowing that we're less than something that diverged doesn't help. If I have something that diverges, it's so big it's infinity, and I know that my thing of interest is even bigger than that, then my thing must have also diverged to infinity. If our thing of interest is below something that we know is so small that the something converged, then ours must also converge because it's smaller than something that converged. So there's really like 4 ways this comparison can get made: converge, diverge, converge, converge, diverge, 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 converge. But only 2 of them help us out. We need to either know that we're bigger than something big or smaller than something small for us to use a comparison to help us out with this guy here. So what we should be able to see here is this. If I were to graph, I guess I can just go back to Desmos here. I'm going to need some graphical help with this guy. So our comparison here is this. I am interested in e to the negative x squared. Right? What I am interested in observing is that there's got to be some simple function that I can judge the convergence of, that I can say for sure is above or below this function. And one of the things I like to think about with e to the negative x squared is that the only thing that's hard about it is the squared part. So what's up with e to the negative x? So one thing I want to say before I go into this part right here. I can first of all see that from negative infinity to positive infinity, it really just looks like we only need to consider the right-hand half of this graph and then double it, right? Because we're symmetric right here. So one thing I'm going to do is I'm going to say, let's just have a first quadrant discussion here, and whatever our answer is at the end is times 2. And that's okay, because notice here if we're trying to discuss convergence, divergence, if this converged to a number, then our answer converges to twice that number. It still converges. If this diverges to positive infinity, then we're doubling positive infinity, and twice positive infinity is also infinity. So the doubling won't affect our convergence divergence answer here. So one, I know I'm not worried about dealing with both halves. Since this is symmetric, we can think about just this one half of the function right here. Again, I'm thinking to myself, I'd like to use easy functions where I can talk about the convergence, like e to the negative x, because I can do that integral. I know I'm confident in my ability with that one. So here's what I'm seeing. It looks like this e to the negative x function is greater than the e to the negative x squared function for 1 all the way off to infinity. And that makes sense to me because e to the negative x squared should decay down to 0 faster. But it doesn't look like it did the job right there. So maybe what we can do is say this. Another function maybe that I can judge should be above this the whole time would be something like, oh gosh, how do I build this quadratic the way that I want it? I'm just picturing like a quadratic, like encasing that guy right there. So let me see if I can be smart and just slider bar around some stuff here. I don't want to horizontally shift this guy at all. I want this to be centered at 0. I do want to flip this guy. What am I doing? Just make this 0. I do want to flip this guy, but I think I want it to be pretty wide so that we go through that point at 1 right there. And my k value should be 1. So I'm noticing here now my purple curve is completely above the blue curve from 0 to 1. The green curve is completely above the blue curve from 1 to infinity. Okay. So here's the way that I'm going to rework all this stuff right here. So we just came up with the formula here of negative 1/2 x squared plus 1 is an upper bound for our function here. So let's go back over to Word and put some pieces together here. Okay, so over the 0 to 1 interval, I'm going to picture, and I'll just use a generic function g of x here. We just looked at negative 1/2 x squared plus 1, right? And this gave us a picture that looked like, there's our bell-shaped curve, and we looked like this, right? So over our 0 to 1 interval, our g of x was above our f of x. So what I can say here is the integral from 0 to 1 of e to the negative x squared dx is less than the integral from 0 to 1 of negative 1/2 x squared plus 1 dx. I know that since the function heights of this one are all shorter, and all that an area really is a bunch of rectangles, that since all my heights are shorter here than here, my total area is shorter here than here, because the widths are exactly identical right there. And by the way, we can do this one really easily. This should become negative 1/6 x cubed plus x, evaluated from x equals 0 to x equals 1. And so negative 1/6 plus 1. So we're getting here 5/6. So I know that this guy right here is less than, in total, 5/6 right there from 0 to 1. Now let's look at the remaining chunk. In the remaining chunk, we have the chunk that goes from 1 to infinity. Here, we're still considering our base function f of x to be e to the negative x squared. And now I'm looking at a new function h of x, and I think that e to the negative x is going to be above f of x for the whole time. Again, my picture here. This function here agrees at 1. So this is my h of x here, and this is my f of x down here. All right, so h of x is above f is greater than h on 1 to infinity. And here we want to say f is less than g on 0 to 1. And so here we showed that g converges and f is less than g, so f also converges over that bound. Here, if we can show that h converges and h is bigger than f, then we'll have shown that f also converges on that little boundary right there. Did I say f? That's right. I was like, what the heck's wrong with my symbol here? F is less than h on that interval right there. So what I want to say now here is that the integral from 1 to infinity of e to the negative x squared dx has to be less than the integral from 1 to infinity of just e to the negative x dx. And when I do this guy right here, I should be getting negative e to the negative x evaluated from x equals 1 to x equals, I'm going to do my bad job right here and just throw that infinity in there. This should be negative e to the negative infinity, uh, let's do it like this, minus uh, e to the 1. And that should be giving me just straight up e right there. And so since g converged and h converged, and they were both greater, and h also converged and was greater than f, on 1 to infinity, it must be that the integral from negative infinity to infinity of e to the negative x squared dx converges. And even better, we have an upper bound on what it converges to. We got for our 0 to 1 piece, we got 5/6. And for our remaining piece, we got, didn't we just get e? So I at least know, based on the comparisons that I made, that the overall total value of this integral is guaranteed to be no bigger than 2 copies, that's our symmetry part, of 5/6 plus e right there, because I found my first part, we found a boundary for it. Second part, found a boundary for it. Found the area underneath both the upper bound functions. And then that was all just 1/2, so we doubled it to get the other half out there. Now, it turns out that we're going to be able to get this a little bit more accurately here if we do some multivariable calculus stuff that we're not doing. It'll be next semester for you guys. But I do just kind of want to show you like kind of how some of these other comparison things kind of work out here for us. For example, the hard thing about comparisons, and we're basically done right here. I'm not really going to like do anything here. The hard part about comparisons is that you have to have a bank of functions that you already know about for sure. And so we know about the 1 over x functions. I know that this guy will diverge. So we know that the integral from 1 to infinity of 1 over x dx diverges. And what I'm seeing here is this is a gross function that I don't really know what to do with it. But what I know for sure is that 1 plus a positive number over x is always going to be more than 1 over x, as long as x is positive, which it is. here x is greater than 1 right there. So 1 plus e to the negative x over x is greater than 1 over x. And so therefore the integral of 1 plus e to the negative x over x from 1 to infinity must be greater than the integral from 1 over x from 1 to infinity dx. And since this diverges, okay. So the trick with our comparisons is you need to be comfortable with the things you already know about, like the 1 over x's, like the e to the negative x's, the ones that we can handle convergence divergence discussion with. And so what you need to be able to smartly do is say, how can I algebraically make a confident statement about how big this function is relative to some other function that I know? The 1 over x versus 1 plus e to the negative x over x. I wouldn't know what to do with this integral otherwise. I don't have a way to manipulate this and make this work out otherwise. But I know for sure that something that's smaller than it diverges to positive infinity. So since this is bigger than something that diverges to infinity, this must always be heading off to infinity then. Yeah, yes, coffee gopher, pardon me, correct. If any part of our integral diverges to infinity, then we say the entire integral diverges to infinity. We want to really avoid doing things like negative infinity plus positive infinity plus natural log of 2 equals natural log of 2. That is a highly unreliable statement there, since infinity is not a quantifiable number right there. It certainly seems to be the case that we have matching symmetric parts in that 1 over x minus 2 graph. But if any component, if any subinterval of our bounds of integration diverge to infinity, then we simply state that integral diverges. Otherwise, we're trying to add and subtract infinite area chunks, and that's a generally discouraged move right there. So comparison test stuff out here. This is a lot more about you being like a smart person in that you can think to yourself, okay, how do I know for sure what kind of inequality I can ever set up right here? And so when we get to the comparison test is going to be one of our most important tests in all of chapter 11, the meat of our last summation stuff that's out there. And so being smart about picking functions that you already know stuff about that you can make generic comparisons for really matters. So notice in this example right here, I was really dependent on Desmos to get some graphical help to know for sure what functions I have that are for sure upper bounds or for sure lower bounds. Same thing over here. I wanted to make algebraically a statement here that says something like, well, this has to be bigger than 1 over x because we're adding stuff to a numerator. So I can say for sure that our expression is bigger than the 1 over x expression for all of the x values of interest, 1 to infinity. Therefore, the integrals must share that same relationship. Therefore, since the smaller of the two integrals diverge, it must also be that the larger of the two diverge. And we can finally make those kind of verified statements right there. So you should really notice that like a lot of what these last couple sections are about is like, well, what do we do if we're stuck? And that's the most important things to know about with calculus, because in most cases in calculus, you get stuck. You can't do the integration, and so use your approximating integration techniques. You can't do the integration, but you still want to know if you're going to get an infinitely large number or not. Well, we should at least be able to directly compare it to some things that we do know if they get infinitely large or not. So there's sort of this always this like constant back and forth in all of calculus that says, since integration is hard, you're rarely going to be able to do it. That means two things. One, you need to have techniques other than just pure integration to be able to handle your thoughts. Two, that means that the few cases in which we can answer integral questions, those matter more to us as sort of like our landmarks that help place us, orient us in the integration universe that are out there. So like on the one hand, it's rare that you're ever going to see an integral that you can truly do. But then you should say, well, then why do we need to practice like learning any of these? And the answer is we develop a ton of our intuition about what we should expect based on these special cases that we can actually handle. 1 over x e to the negative x. Those are great bounding functions for some other important, more difficult functions. And so these really help orient us in the land of integration that's out here. So in the interest of staying short here, I'm still at an hour and 15, a little bit long, still shorter than normally, whatever. We're right on time for a regular class here, hour and 15 minutes. So I'm going to call it right here. Tomorrow, we are going to pick up with arc length. I'm going to give my 60 seconds on arc length right now. Arc length is easy because the length of a curve, we can just break down the curve into being lots of little subsections of straight line pieces. We can use our distance formula to compute the distance of a straight line piece. We will then allow the number of subdivisions to get infinitely large, our subdivision size to get infinitely small, and we will add up, integrate up all of the pieces that we see from our distance formula. So for 8.1, you should expect kind of easy concept. It should be the integral of the distance formula is the arc length of a curve, and that's essentially what we're going to end up seeing out there with some light modifications. So I'm going to get some homework posted here for you guys for this week here. We are covering 3 sections this week instead of 2, but I think they're all pretty okay to deal with. Today is just like, hey, remember limits. Tomorrow is like, hey, remember how integration works? Do you add up lots of small things to get a big thing? And then the third day will be surface area, but we're going to see that just extends really nicely from our arc length argument as well right there. So 8.2 shouldn't be any big thing either. I'm kind of trying to make sure that we can do a couple of easier days for our slightly more interesting chapter 8 topics out there. Um, yeah, cool. All right. Happy 7.8, everybody. I'm going to get the 8.1 stuff going tomorrow. And then I think we'll do 3 videos this week. So I think I'll do a third one on Wednesday as well there. So I will see you guys for round 2 tomorrow. Have a